Good morning, it is me, the Div3 machine, back where I belong, doing contests for people rated under 1600. Today we have round 874 and some Greek yogurt. Let's get started. 2 hours, 15 minutes. All right, 10-minute penalty for a wrong submission, which means it counts as if it took you 10 more minutes to solve a problem. Okay. We have a sequence of notes of the characters A through G, but we can record exactly 2 notes at a time. He wants to obtain melody S. He can merge the recorded melodies together. So the last sound... The last sound of the first melody must match the first sound of the second melody. Oh, so you need to know A, B, and B, A. And then A, B, B, A, A, C. Okay. Yeah, I see. Yeah, so this needs to be A. Then we need int n equals this, and then char array A, new char array n. We'll have a hash set of string st, new array set equals new hash set. And then we'll print out.println set.size at the end. And for int I equals 0, I plus 1 is less than n, I plus plus. We will print, or we'll add a at I plus a string, turn it into a string, plus a at I plus 1. And that should be good. It'll make things bigger. Just a second here. Number format exception, where? New line. 24164 looks good. Submit. A. Next problem. B, C, D, E, F, and G. All right. Problem B, restore the weather. You're given an array containing the forecast of the weather for n days. That is, AI is the estimated air temperature on day I. You're also given an array B, the air temperature that was actually present on each of these days. However, all the values in B are mixed up. Determine which day was which temperature if you know the weather news differ from the actual forecast by no more than k degrees. Ah. Oh, okay. This is like hard. Wow, yeah, okay. This is a really hard div 3b. Like, it's not hard for me, but like the implementation here is kind of tricky. Static class pair. We need the int index and then int value. And then public pair int index int value. This dot index equals index. This dot value equals value. We'll make it so that we can sort this pair by value. Public int compare to pair o integer dot compare value o dot value. Okay, so now we have all of these pairs. So we need to read n equals this, k equals this. Oh wait, it's not. We can just sort both of them, right? like it's always possible. Okay. We don't need K. Yeah, so we'll make this a new pair array n. Then B will just be an array of size n. And then we'll sort B. And we'll also arrays.sort the A pairs. Oops. So we've got both. And then we want to mark, first we need a copy of this. So we'll have pair array order equals new pair array equals, sorry, ap.clone. All right, and then we'll say for int I equals 0 less than n I plus plus ap at I dot index equals I, and for int I equals 0 less than n plus plus out dot print. This will be b at ap or at order at I dot index. Space. That's hard to read. Oh, wait, am I? No, that should be fine. Ah, 777. Yes, that's fine. Yeah. Maybe this is just right. 225411. Okay. 04 minus 1 0. Yeah, okay, it's fine. Yeah, so it's a good problem, but it looks really hard. All right, we can't submit. We'll move on to C for now then. Given an array A of n positive integers, he wants to build an array B of length n. Okay. He considers an array beautiful if all of the numbers in it are positive and have the same parity. To build the array B, he can assign each bi either ai or ai minus aj, where j is some value from 1 to n. So you can either have it be the normal thing, or you can be the normal thing minus something else. To avoid trying to do the impossible, he wants to ask you whether it's possible to build a beautiful array B of length n using this array A. So all we care about is the smallest odd number, and then we should be good from there. Oops. Huh? I don't know how I got here. Okay. Doesn't matter. We can keep going. Okay. So int array a fs dot read array n int min odd equals integer dot max value for each thing in a if a is order doesn't matter, right? So we can just say if a is less than min odd and if I mod 2 equals 1. Is everything initially positive? Yeah. Then min odd equals I. Okay. And now Boolean works equals true by default. So if I mod 2 equals 1, then continue. Otherwise, if I is greater than min odd, then we're good. Oh wait, so this is, can we make it all odd? Otherwise, yeah, works odd equals false. So maybe we can do works odd, and then we also have Boolean works even. So that would have to be 0. Yeah, I guess we can just say works even equals false. I don't think you'll ever, I don't think this ever matters in works even, because min odd will cause problems, but let's see. Looks good. Let's submit. See how are our submissions before. Correct and correct. All right, on to D. Me and my yogurt have a permutation of length n. Permutation is an array consisting of n distinct integers from 1 to n in any order. For instance, we know what a permutation is. For the permutation P, you need to apply the following exactly once. Choose a segment of numbers and reverse it. Okay. Then swap the prefix and the suffix. Wait. So reverse and swap it, the prefix and suffix. So this is the same as flip the whole thing, flip the prefix, flip the suffix. Okay. Yeah, so first we reverse the entire array, and then we reverse the prefix and suffix. Okay, they don't intersect. We need to output the lexicographically maximum permutation that can be applied in the above operation exactly once. It's not too bad, actually, because we just are going to move the 5 to the beginning. Okay. Yeah, so this is not actually that hard of a problem. All right, let's think. So we first start by reversing the array. Now what we have left is we're going to reverse a prefix and a suffix that don't overlap and don't include how big can the segment be. And don't include at least one number. All right, so priorities are, firstly, we need to move 5 to the beginning. We have lexicographically maximum permutation. Yeah, so we need to move 5 to the beginning. So this tells us exactly where our prefix should end. Unless 5 is at the end. Or, yeah, unless 5 is at the end. Yeah. If it's not at the end, we're good. Okay. Priority number 2. Everything that's now before 5 is fixed. So we want the biggest thing, and also the thing after 5 is fixed. Well, yeah, in this case, if these are all fixed, and then we have some numbers here, and then we're going to pick a range to reverse. Really, all we care about is like the biggest range that does something good for us. Where like this O improves. Yeah, and that's the second range. Okay, and then what do we print the array at the end? Okay, so we need static void reverse int array a int l int r. Yeah, so int array new a equals new int array n. If, actually, yeah. I'll have int array temp equals new int array, so be r minus l plus 1. And then for int I equals 0, t dot length I plus plus, t at I equals a at l plus I. Then for int I equals 0, less than t dot length I plus plus, a at l plus I equals t dot length minus 1 minus I. And then we will return nothing. Okay. So now you can reverse something. So we'll get int array a. First we need int n. Fs start read array size n. And then we can reverse the whole thing. And then we need to find this prefix. Okay, so int array index of equals new int array n. So the index of at the thing at a at I is equal to I. All right, so now we need to do priority 1. So if a at I is equal to, or sorry, if index of n minus 1 is equal to n minus 1, it's kind of annoying. Index of n is equal to n minus 1 because 1 based. Then we are indeed looking for 5. Then reverse. And index will be index of n plus 1. Okay, so now we have this. So now we need to reverse A from 0 to end index. And then we need, yeah, so int swap to start will be end index plus 2, while swap to start is less than n, and A at swap to start is less than A at n minus 1, and swap to start plus plus. And then we want to reverse, if swap to start is less than n, we want to reverse from A from swap to start to n. And then we should be good. Okay, and then what happened? That's never good. Ran X out of bounds exception? N minus 1. 4, 5, that's not right. Yeah, no, that's not right. 5 should be in the beginning. Oh boy. Okay. Hi. And index 0? Huh? Doesn't make sense. Why? Ah. Because my logic is backwards. Okay. Now we should be good. Let's just submit. Now run samples, I guess. Man, did that really take me 12 minutes? Oh my goodness. Okay. 3. Oh, darn. Unfortunate. What? What? Wait. Oh, okay, we're good. So 3 goes to the beginning. Now 4 is at the end. Okay. Ah. Wait, no, that's fine. Okay, to string A. So we have 3, 1, 2, 4. Okay. So we want the first index after 3. Oh, we knew empty. Ah, okay. That's a tricky case. Yeah, so if it's already in the beginning, we should do nothing. Yes, okay, so if end index equals 0, end index minus minus. Should be 1, not 3. Why 3? Ah, well, it's greater than. Okay. It's a slow day, what can I say? Alright. On to E. Rain dance. And people came to the festival and decided to do a few round dances. There are n people in the round dance, and each person has 2 neighbors. If there are 2 people in the round dance and they share, so if 2 people in the round dance, if there are 2 people in the round dance, they have the same neighbor on each side. What? Each person has 2 neighbors? Oh, they're just explaining how this works. So you have a bunch of people in a circle. Okay, anyway. How many dances are there? A participant of the holiday remembered exactly 1 neighbor. Your task is to determine what the minimum maximum number of round dances could be. What? They did not explain anything here. I don't understand at all. If there are 6 people on holiday, so there are 6 people on holiday? What does holiday mean? Is that just the number of people there are? Okay, you have 6 people. Just at all. Not on holiday, just at all. The numbers they remembered are equal to this. Wait, what is the holiday? Where did the holiday come up? Holiday just doesn't matter? Each person of the holiday, so this whole thing's a holiday, I guess, remembered exactly 1 neighbor. You need to determine what the minimum maximum number of round dances could be. And the maximum is 3. What are we talking about? What is a round dance? There are at least 2 people in the round dance, and each person has 2 neighbors. If there are 2 people in the round dance, and they have the same neighbor. If there are two people in the round dance, then they have the same neighbor on each side. Okay, this is a terrible problem. Next. Ira loves Spanish flamenco dance very much. Oh my goodness. Give me an author who didn't write a problem about Spanish dances. Okay. You have a pet chinchilla. Oh my god. Alright, so you have a pet, a tree, and N vertices and huge scissors. A tree is a connected graph without cycles. During a boring physics lesson, this person taught about how to entertain her pet. Chinchillas like to play with branches. A branch is a tree of 3 vertices. Okay. A cut is the removal of some edge in the tree. This person has plenty of time, so she can afford to make enough cuts so the tree splits into branches. Is that always possible? What does the chinchilla have to do with this? Okay. Okay. All right. So the question is, can you turn this into branches? So afterwards, every node either has degree 1 or degree 2, and it's 2 colored. So all of the red nodes have degree 1. Can it have nothing? Yeah, no, okay. So every node has to have degree 1 or degree 2, and it's 2 colored, and all the red nodes have degree 1. These ones are red. This one's black. This one's red. Ah, so it is actually 2 colored. Ah. Yeah, that's cool. All right, interesting. Let's do this. This is a good problem. This is really clever. All right, so observations. So 1, it is actually 2 colored. All right, so now we have a 2 colored tree. What do we do from here? So we can say we need to make 1 color we need to do this. Is it just yes or no? It is to be cut. That's a little annoying, but it's fine. All right. So if 2 leaves are different colors, then it's impossible. Even if all the leaves are 1 color, it might still be impossible. Okay. Static class node. So we can do a tree DP to solve this, which is probably the solution. But if it's at like this place in a set, this isn't even E, this is G. Whoa, that was cool. Wow. Neat. It renames it for me. Alright, nice. Yeah, so we can do a tree DP. Is it easier to do anything else? Can we just go bottom up? Can we just do a DFS instead? How do you want us to print these edges? Just the indices. Multi-test case. So I'm not really sure what to do about this. I think just the DFS will work. Yeah. We should only have one choice. If we do a DFS. Okay. Yeah, alright, so we'll do that. So int n equals this, and then node array nodes equals new node array n for int I equals 0 less than n plus plus nodes at I equals new node. Each node needs an array list of edges, I guess. New array list. And then we need to have array list edge to cut. New array list. Let's make this static. And then we'll print this to cut dot size and out dot print line for edge e into cut out dot print e dot index plus 1 plus a space and then out dot print line. All right, and then we need to do the DFS. We'll reset these screen test cases. Okay, and then we just need to do the DFS here. Okay, so this shouldn't be too bad. It should only be a matter of doing it for each kid. E dot, what is this? Of this dot DFS. Oh wait, it's always possible, right? We might just need to keep the parent. It might not always be possible. Yeah. Okay, so each one of these needs Boolean is 2, and then a Boolean push up. Okay, so if, what do we need? We need edge E. Keep 1. Yeah, okay, so we'll have all of these. So this is node O equals E dot O of this. All right, so if O dot is, I guess all we care about is push up. So if O dot push up, then we need to handle it. So if keep 1 is not equal to null, then keep 1 equals E. Else if keep 2 is not equal to null, keep 2 equals E. Otherwise, we are in trouble. Okay, so yeah, we've got this. All right, so now it does not need to be too colorable. So this is just not true. This is also not true. Yeah, okay. This is nothing to do with two coloring. All right, yes, so we do this. Now we need to consider return policy. So like a target. So if keep 1 equals null and keep 2 equals null, then yeah, okay, so if this edge is not pushing up, then we need to say edges, this one to delete, to cut dot add E, and then we're good. We also need edge from E, and then if E equals from, then continue. This will be null. Okay, so otherwise cut it. So if these are both null, push up equals true. Else, if keep 1 is not equal to null, and keep 2 okay, so, well, yeah, otherwise we know keep 1 is not null. So if keep 2 is equal to null, then push up equals true. Otherwise, we might not need to push up actually. Keep 2 is equal to null, and keep 1 dot other of this dot is 2. These need to match up. So if keep 1 dot is 2, or keep 2 dot is 2. Like if it's 2, it should never be pushing up. Yeah, okay. All right, fine. But that's not true. So, yeah. Okay, so otherwise this is keep both. So I'm keeping just 1. This is not true. So if keep 1 dot O of this dot is 2, so if it's a 2, I need to be a 1. And this is good. If it isn't a 2, yeah, if either of these are a 2, we're in trouble. Okay. We push up and then we say is 2 equals false. Okay, otherwise we keep both. Okay, otherwise is 2 equals true, push up equals false. Okay, I think we're good. Let's try it. Ah, yeah, so what if it's impossible? Need to read in the edges. How are the edges formatted? Like this. So then 4 int I equals 1 less than n plus int a equals this minus 1 b equals this minus 1. Edge e equals new edge from nodes at a to nodes at b, and it's I minus 1. A dot edges dot add e, and then same with nodes at b. Darn. Just try one of these. Why is it -1? Okay, so Well, that's a bit concerning. How can these both be null and this be false and false? That is what I read, right? Null, null, false. Oh, false, true. False, true. Oh, if keep 1 is equal to null. I'm an idiot. If keep 2 is equal to null, then we should be good. Okay. All right, that part is done. Let's get this case. Zero, zero. So the first one we get wrong. Oh yeah, because I'm not checking push up on the root. Where do I do nodes at 0? Yeah, so if nodes at 0 dot push up, then impossible equals true. Submit. G. Should be good. Okay, that took way too long, but I think we finally got it. Okay. All right, problems. Let's do F. Okay, so we have a flamingo dance. We're starting our own dance studio with N students, the ith of whom is level AI. We can choose several students and set a dance with them. She can set a huge number of dances, but is only interested in the magnificent dances. It's magnificent if it has exactly M students in the dance. The levels are distinct, and 2 dancers have a difference of any 2. So there's... What does any 2 mean? Of any 2. So is this some 2 or of every 2? These are magnificent. These are magnificent. Why are they? Exactly M pairwise students. The levels of all dancers are distinct. Levels of any 2 dancers. They're, I think you mean every 2. Let's say clarification request here. Level of any 2 dancers, yeah. Yeah, okay. So in this, only 2 participate. Yeah, so, okay. So I am right. It might be kind of large. I don't think it's going to be that large, though. So if M is big, it's just impossible. M cannot be bigger than 10, 9, 8. So 6 times 5 over 2. This is for 6 people. And that's how many things you have. Right? How many pairs? How many dancers are there? M of different levels. Differing by less than M. Oh, so you don't care about the number of pairs at all. Okay. Oh, so this isn't actually that bad. It's just how many things are in this range. So if we just brute force the minimum value, we just know how many things are to choose from. Okay. Yeah, we can do this. How big do the values get? Big? Okay, fine. Okay. That part doesn't matter. No thinking required. We need int n. Okay, and then we need to say int array a, read array size n, and then we can say we need to let's ruffle sort this. And then we'll say hash map of integer to integer map equals new hash map. I have int count. This needs to be a tree map, actually. Count equals 0. So we'll put I in count. And then for int I in key set, in map.keyset. So int max would be I plus we need to choose at least one of these current things. It's a bit tricky, okay. Because if we don't pick any, we would double count. Okay. Translation troubles. Thank you. No worries, no worries. Okay, let's do round dance instead. I don't actually know how to do that. Yeah, round dance is probably easier. And people, yeah, geothermal probably did this, solved this an hour ago. Man, how are people so speedy? Okay, let's get E. And people came to a festival, have some round dances. There are at least 2 people in each dance. Each person has exactly 2 neighbors. Okay, so yeah, so you do have some circles. Yes, if there are 2 people, they have the same neighbor twice. Okay, we want to find out how many dances there were. There are at least 2 people in the round dance. So the neighbors are 2, 1, 4, 3, 6, 5. So 1 has a neighbor to 2. 2 has a neighbor to 1. Then 4 and 3, 6 and 5. So the minimum might not be 1. How's that? 2. Okay. This goes to 3, 3 goes to 1. Ah, so you can have a cycle. Yeah, so you can... This could be arbitrarily big, right? Yeah. You also might not have any freedom if you have a cycle of length bigger than 3. So basically just the 2 cycles are free. Ah, but the 2 cycles only fit in with each other. Yeah, so this is pretty easy. Cool. Yeah. All right. Let's get this. Then we'll move on to F. E. Okay. So E has int n, int array A, read array n. And then we need the cycles. So we'll say Boolean array hit, new Boolean array n, and then array list integer sizes, new array list, and for int start equals 0, start's less than n, start plus plus, if hit at start, then continue, and then int size equals 1, while not hit at start, then hit at start equals true. I guess we'll make size equal to 0, and size plus plus. We need int at equals start, so we don't mess up what we've got here. And then at equals a at, and then size, and then sizes dot add size. Int to count equals 0. Int n non 2s equals 0. I hope no one can dance with themselves, otherwise my solution doesn't work. It also doesn't make much sense. Chicken dance. Yeah, okay. So we should be good here. So then we just need 2 count, non-2s, Yeah, so the min would be zero, otherwise one. And then the max will just be the 2 count. Is there something I'm not thinking about? Let's see. Uh-oh. One, 3, 2, 3. Oh, this one. Third one. It's more complicated. Why is this? Because we have a pair. Ah. Yeah, okay. So we need the number of things that are open. Okay. I see. Int n open. So this is really n. Yeah, we don't need this anymore. We also don't need sizes. Yeah, we don't need sizes. This is b n. What did I do with n? It's not even close. Why did I say n? N open plus, oh sorry, it's n closed plus n open is equal to 0, 0, otherwise 1. This is n closed plus n open. Okay. And we need a hash set of integer out, new hash set. Okay, so while each of these things, then we can say if outset.size equals size, then n closed plus plus, else n open plus plus. Three, 3, 1, 1. What? This one is 1. That's 1? 1, 1? Okay, I'm very wrong here. 1 dances with 5, 5 dances with 4, 4 dances with 3, 3 dances with 4. This dances with 1, this dances with 2. So they are all connected. Yeah, because it's a Cthulhu graph. I should have seen this coming. This is really basic. I should have seen this coming from a mile away. I don't know how I didn't consider this. All right, so this is all... Yeah, so my solution is totally wrong. Well, like the idea is right, but it's just the n open and closed. How do we want to check if a component is open or closed? We can do a BFS. I guess we just take n steps and see if there's a duplicate. Might be easier. Okay, yes. So we have this. We also want int array size. Size equals new int array n, arrays dot fill. Size with 1, and then we'll say size of A plus equals size of B, and size of B plus equals size of A. All right. This is largely unhelpful now. Yeah, so then we need disjoint set dj new disjoint set n. Union a at I with I. Okay, so in size will be dj. So if dj dot find start is not equal to start, then continue. Otherwise, int size equals dj dot size at start. Int at is start. Equals a at. And then hash set integer set new hash set. So we take the cycle, and then if size equals set dot size, then n closed plus plus, else n open plus plus. Okay, finally, do we have the solution to this problem? Not even close. So we're marking everything as closed. Or it's size 2. Okay. So the idea behind the problem was very good. The wording was not, but I really like the idea, which is not always easy to get right, to be fair. All right, this person loves Spanish flamingo very much. She, yeah, what was this again? Oh yeah, how many? This counting problem. Okay, so we can get what the next thing is we want to know how many ways are there. So we have like some number of students. How many ways are there of doing this? We want to make sure we include one of these students. So we can just say with one of these minus without one of these. Yeah, okay. So it's actually pretty easy. So for each key set, the max will be I plus M minus 1. Okay. And yeah, so int total. So int equals min equals map dot get I. Int total will be map dot floor entry of max dot get value so we have minus equals minus below min yeah, we need below min. Are each of these positive? Yep. Okay, so you have floor this, step before min. That's how many there are total. Minus before min. That's how many there are here. All right, so now we just need n choose k. So let's pre-comp. Pre-comp our factorials. And then we need long ants equals 1. One way of doing it. Choose no one. 0 ways of doing it. Out dot print line the answer. And ants equals ants dot add, or equals add the ants and choose k. How many are there? Total. Choose m. Sub. And choose k. Total minus equals min. Choose m. So how many ways are there to do it? Minus how many ways to do it without using this min. And then I think we're good. Yeah, one thing is we just have to make sure n choose k always works. So k is less than 0 or n is less than k, return 0. Huh. Ah. Let's do just this, I guess. I say the answer is 4, but the answer is 2. Am I just double everything? Nope. Oh my goodness. I need this here. All right, for 2 adding 4. What are the 4 ways? So 2 plus 3 is 5, right? 1, 2, 3, 4. So we cannot choose any of these. That is 4 different ways. Oh, they all have to be different. Wait, what? They all have to be different? They're all different. Dang it. So it's not even that big, right? Oh, it's just the product of them. Fine. Fine. I just solved the wrong problem. It's always infuriating. Okay. This is F2. Okay, so that's just completely the wrong problem. Not even close. Now we just need to know yeah, so how do you solve this problem? So we have no other problems left. So we need to say I solved the wrong problem. The problem does not exist on the problem set. I did it correctly though. Okay, so they all have to be different. That just means we need the products of how many of each of them there are. Yeah. So we just need we'll just coordinate compress. Wait, yeah, so you have to use m things, and they have to be pairwise distinct, and they have to have a difference less than m. Yeah. Oh, they fixed it. Thank you. Yes, so we'll just say get 8i. So now this is compressed. And now we need the count. Oh, this is map.size. So int I and a count at I plus plus. Okay. And then we need long array product equals new long count plus 1. I equals 1 less than, we'll say prod at 0 equals 1. Less than prod dot length I plus plus. Prod at I equals prod at I minus 1 times count at I minus 1. Okay, we have the cumulative product. Ah, that's kind of annoying though, because if it's ever 0, we're in trouble. Should we just do everything that's not a 0? Now we have all the zeros. Okay, for int L equals 0, L is less than count dot length. This also needs to be multiply because we need to use our mods. Okay. And what here? So for each left, int next 0 equals zeros dot ceiling L. If next 0 is greater than or less than or equal to L plus M, or less than, I guess. Then continue. Otherwise, long range product equals prod at L plus M minus prod at L divided by. B to the mod minus 2. All right, range product. Yes, and then I think we're good. And then ants equals add ants range product. We need this case. And then we need to print the answer. All right. Very cool. Hundredth in the world. Not bad, not bad. Can't complain. Yeah, let's talk solutions real quick. So I was actually pretty fast on A. Wow. All right, let's talk solutions. Yeah, so in this problem, you have some string, and you want to count how many distinct pairs of letters there are, like adjacent pairs. So in this example, you have AB, you have BA, and you have AB again. Since you had AB earlier, then you don't count it a second time. So you only have AB once, and then you have BA once. So the idea is, the idea with that, I guess, is that you can use a hash set, or you can check if your array of all of the pair letters already contains it. I can show you, hash sets are useful because they don't contain duplicates, so I can show you how to do that. So the idea is you have a hash set of all of these things, and this turns it into a string. So you have, I turned it into a character array here because it's shorter than .char@. And then here, this turns it into a string, and then I add the two together. So this will give me that pair, like AB, for instance. I add it to the hash set, and if I ever add a duplicate, the hash set will automatically remove the duplicates. So at the end, set.size is how many unique things there are. So hash sets are great for this. Yeah, that's the solution to problem A. I'll talk about B, C, D, E, F, and G. All right, B. Yeah, so for this one, they get pretty close to each of these days, and you want to find a way that it's possible, and they guarantee there will be some way of doing it, I guess. So the observation is the day where they guess the smallest thing, that should also be the day with the smallest temperature. If it's not, it's just going to be easier for you down the line, right? The only way you'll have a problem is if you don't match those things up. So, as an example, this first day, they predict temperature 1, and we should say that matches temperature 2. So that's like the idea. And then the next smallest is 3. We should say 4. Then 3 again, we should say 5. And then 5, we should say, well, I'm off by 1 here, but you get the idea. So the smallest prediction should match the smallest day in the output if we want the biggest difference to be minimized. If we invert them, we'll just keep things the same in the best case, or in the worst case, we'll make some difference bigger and some other difference maybe bigger, maybe smaller. So yeah, that's the observation here. You can prove that, but it's pretty intuitive as well, I think. I had a proof in my head that relied on, like, if you wanted to break this, how would you do it? And you would do it by, you run out on one side, right? So eventually the problem, like, it was a recursive proof in my head. And eventually it was like, it's the smallest thing in the array that's going to end up breaking you. So if you match everything, then that's going to be the best you can do. As far as how you code that, it's a bit tricky, to be honest, especially for a diff2 problem. So I used this pair class, and I sorted them by value. And this pair was the index of everything in the first array, and then the value of everything in the first array. So if you go up here, I have the index of everything and its value, and I make it here. So this is my array of pairs. And then B is just an array of integers. And then I sort both of them. After sorting it, I update the pairs, but I keep a copy of the original order. So this was the order that things were in before I sorted them. And then I can go through the original order and print the B at this new index, the index that it's at now, in sorted order. Yeah, so you can do this also with lambdas. If you want to sort an array by something else, you could do it with that. I thought this was the easiest in my opinion because I'm super comfortable with doing this, but you can do it in a lot of different ways. But yeah, I think this is a good way of doing it. Maybe not the shortest though. Okay. All right, problem C. Beautiful array. What was this problem? Ah, this one. Yeah. So everything needs to be positive and everything needs to be the same parity. So there are two different ways you could do this. The idea is you could either make everything odd or you can make everything even. Now, making everything even is just everything starts even. I think it's just that simple. To make everything odd, though, everything either needs to be initially odd, or if it's initially even, it has to be bigger than the smallest odd number in the array. So those are the two conditions. Either everything's even, or if not everything's even, everything needs to be bigger than the smallest odd number in the array, or it needs to be odd. And if you check those two things, one of them will work, and that'll be your solution. So this checks to see if it works with everything being odd by making everything odd. This is a more complicated check than it needs to be to see if everything is even. I just get the minimum odd thing beforehand. So yeah, hopefully that makes sense. As far as why you'd use the minimum odd, right, it doesn't matter which odd number you'd subtract from, because no matter, like, subtracting an even won't change whether or not something is even. So it only matters to subtract odds. And if you're going to subtract an odd, if all that matters is whether it's even or not, and whether it's positive, you want to subtract the thing that has the best chance of keeping it positive. So that's why the greedy approach works there. All right, problem D, flipper. You have a permutation of length n. Ah, yeah, this one. Okay, so what they tell you to do here is you have some part in the middle. They tell you to flip the part in the middle and then to swap the prefix and the suffix. That's fine. You can solve the problem like that, but there's an easier way of thinking about the problem. So let me explain this here. So let's say you have this array initially. They tell you, let's say you pick from here to here. So we're going to pick the 3 and the 1. So what they say is you're going to reverse the 3 and the 1. So now you got 1, 3. And now you're going to swap what's in the beginning from what's in the end. So this part goes to the beginning and the 2 goes to the end. So this works. An easier way of thinking about this, though, is instead of thinking about like moving pieces of the array around, we're instead going to think about just doing reverses, just doing range reverses. So instead, an equivalent version of this is we're going to reverse. So like, let me show you how many times each thing gets reversed. So this thing, the 2, gets reversed twice. The middle part gets reversed once, and this part gets reversed twice. So basically, this is the same as reversing the whole thing. So if we reverse the whole thing, then we get 4, 5, 3, 1, 2. And then reversing the prefix, and then reversing the suffix. But it's nice because reversing the whole thing is the same no matter where you choose these split points to be. So basically, if we imagine the array starts being reversed, we just have to reverse a prefix and reverse a suffix that don't overlap and have like one thing between, but the prefix and suffix can be empty. And then after we do that, we just want it to be as big as lexicographically maximal, which means we want the first element to be as big as possible. Among all ways of doing that, we want the second element to be as big as possible, and so on. So yeah, so that's the easier way of thinking about it. And then as far as once you're here, how do you make progress even more? We want to say, can we get the 5 to the first position? So in this case, you can, right? So if we started with this, if we want to reverse the things before this, that's really easy. So we'll just like, we pick a split point, we reverse these things. So the last thing in this array will become first, which means we want to pick the split point just after the 5. And we can always do that. The only case we can't is if 5 is the very last element in the array, in which case we can never move 5, right? Or like we could kind of move it, but we're interested in what the first thing in the array is, right? And we can't ever make that first thing a 4 or 5, so we'll make it a 4 instead. So if we have something where, like, let's say once we've reversed it, this is a 2 and this is a 5, and now we have to pick what our two split points are to make this minimal. We can't make this the best, so we'll put 4 in the front. Maybe we have actually 2 here and 4 here. So if we have something like this, this will be our prefix that'll get reversed. So it'll start with 4, 2. And then we'll maybe reverse one of these things. Maybe here, maybe nothing, to make the end as big as possible. In this case, we would pick an end here so that we get 5, 1, and that's bigger than 1, 5. Okay. Yes, there is only one other weird case. So yeah, so we pick this either after the 5 or after the 4. So after n or after n minus 1. And then for the tail part, what we just want to do is pick the biggest one that helps us. Because every number is more important than all the numbers after it. That's just how, like, lexicographically maximal works. So if we want to make this one bigger, even if we make everything else after this smaller, which maybe happens, I don't know. It's always beneficial to focus on this one than everything else after it. So we want to pick the biggest range where some element is smaller initially than the last element in the array. So if we have like 1 and then some other stuff here, since 1 is smaller than 5, we want to reverse this. Even if, like, I don't know, whatever. No matter what happens, if 1's smaller than 5, we want to reverse it here. So we'll pick split point here. Otherwise, if this is like a 6, then 6, 5, this would increase. So this would actually hurt us. So we wait and then we consider this one. Like, would this help us or not? Yeah, that's the idea. There is one other weird case, though, that you got to be careful of, and it's in samples. So it's not actually that scary. But it is, what happens if you have one of these cases? So what happens if you have a 5 at the end and a 2 here? Exactly. So if you have this, then what? So if you have a split point here, right? Okay, so first of all, if you have this, we can't move 5 to the beginning because we have to choose a split point so that the two split points have, like, at least one element between them, because that's the range we pick in the problem. So we can't move the 5 to the beginning because we can't pick our prefix to be the entire array. So we'll pick 4 to be in the beginning. So we'll make our prefix here. Well, this actually might not be optimal because this thing we might want to move to the end. And we actually can do that if we make our prefix the empty string instead. So we also have to consider that. We might want to make our prefix the empty string. And that is helpful if only the first element is, like, what we're looking for. So if the element that we want to move to the beginning is already at the beginning, we'll choose the empty prefix instead of the prefix of one element. Because we're not changing anything anyway. And that's the last observation here. So here's what the code looks like. We just do this. So we find the index of everything. And once we have everything's index, then first we reverse the array. Then we get the index of everything in this reversed array. Then we find the index of the thing we want to put in the first position. We reverse that part. And then we keep walking through until we find a place where we are benefited by this swap. And then we make that second swap of the end of the array. Okay, yeah, that's the idea to problem D. Long explanation, but I think it works. Round dance. This is a very confusingly worded problem. Let me do a better job wording it. So basically, yeah, you have the following. You have a graph of red nodes with some red edges. Yeah. And every red node has one outgoing red edge. It's like this. And there's also a graph on the same nodes with some blue things that have a bunch of cycles. Let me do something more interesting. Here's a more interesting case like this. Okay. So this is the red graph. You also have a bunch of cycles. So maybe this is what the original graph looked like. Maybe it looked like this. So in this blue graph, we have a bunch of loops, each having at least 2 nodes in them. And in every loop, every node has degree 2. So in this case, we have this cycle here. In this case, we have a cycle of nodes that are of length 2. And the way we got the red edges that were given in the input is for every node had like 2 outgoing edges, right? So this node here had these 2 edges. We picked one of them. So in this case, we picked this one to go here, right? In this case, we picked this one to go this way. And now the question is, if we're given some set of red edges, what is the most and the fewest number of blue cycles that originally existed? So that's the problem. If you didn't understand it before, that's the problem. For some given set of red edges, what is the most and fewest number of blue cycles that originally existed? Yes. Okay. So how do we solve this? We're going to look at like 2 types of cycles. One is one that I'll consider open and one I'll consider closed. So a cycle is open if you can theoretically combine it with some other cycle. So if you ever have like something like this, where you don't know who matched with this person. Wait, am I even understanding the problem right? Oh yeah, I guess I am. Yeah. Okay. So, yeah. All right, so it's something like this. Yeah. So that is the correct problem, I believe. Though I could be incorrect. I think that's what the problem is actually describing. Solution idea is the following. If a graph has something like this, if it ever has 2 nodes with an edge between each other, that means this node might have some other edge like this. And this could be anything. It might be just this thing here, but it also might not be. So yeah, that's a bit interesting. And man, okay. Honestly, I don't know how to describe this problem. I don't understand what they were asking. This is terribly worded. So I'm going to skip the explanation of E. I'm sorry. Yeah, I don't know. I don't know. I don't know what he's asking. All right, I can explain the other 2 though. F and G. Yeah, let's talk about F. This is like very difficult to put into words. So, all right, here you're also doing a dance, and this is just a counting problem. So you want to say, how many ways are there of picking M people, where all the people have distinct skills? Yeah, have distinct levels. And also, for the group of people you pick, the difference between the biggest and the smallest one is less than M. So basically, you're going to pick a group of people, and the people have to have values like 5, 6, 7, 8. And that's it. You can have no duplicate 5s, no duplicate 6s, no duplicate 7s, and no duplicate 8s. So it has to be 5, 6, 7, 8. How many ways are there of doing that for every consecutive range of numbers? Yes. So in this case, we're picking 4 things. We can do 7, 8, 9, 10, or same 7, 8, 9, but then with this 10. That's the idea behind the problem. So you can also do it with the 6. So maybe there are more ways. Yeah, 6, 7, 8, 9, and then you also do 10s and 11s. So okay, in total there are 5 ways possible. This one's more interesting. We're picking 3, so we do 2, 3, and 4, or this 2 is same 3, same 4. Yeah, that's the idea. The solution here is to basically brute force the left endpoint, and then we want to see 2 things. First of all, is there a 0 in the range? And if there isn't a 0, what is the range of this product of numbers? So we can do this using modular division. I actually have a video on modular division from when I was quite a bit younger, but you can look it up. It's like second thread division under mod. And the key observation is, yeah, this is the same thing as prefix sums, except we're doing it with multiplication and division instead of addition and subtraction. So the code for that looks like, I guess I'll show you my code for E. Yeah, I may have overcomplicated it. Yeah, okay, whatever. Problem F. Yeah, so I sort all of the things which I don't need to do. Wait, what? Am I solving? That's the wrong problem. Okay, this one. Yeah, so first things I do is I compress all the values. Key observation here is we are allowed to do this because if there's something that occurs 0 times, then it will like invalidate the things around it. So if we have no 5s, for instance, coordinate compressing, as long as we keep a thing around, like let's say we have some 3s, we don't have any 5s, and then we have some 6s. It's okay to compress things and get rid of the 5s as long as we like make sure to note we have no 4s. And 4s are important because they're next to the 3s, right? So for every time we have a value, as long as we keep itself, the thing 1 less than it and 1 bigger than it for every value, we're never going to like add possible answers that didn't originally exist. So that's why I'm compressing here. And that makes me like get to use arrays later, which makes my code much more convenient. But I guess in C++, if you can do like array access with set operator, then it's fine. You don't even need to do that. But I thought this was clean. We don't need to sort this array, so that's unnecessary. But ooh. Oh, that's fine. Okay. Yeah, I keep mixing up my ruffle sort with a linear sort, radix sort. Because radix sort, this would be a problem because we have multiple test cases. Yeah, so now, okay, so this like compresses everything. So now I can compress everything into the original version. So now if I have an array that looked like 1, 5, 10, then this array would be 1, and then I would skip 1. I would skip 2 because it's next to 1. I would skip 3 because it's next to, because like 3 would be 4. Then I have 5. Then I would skip 6. I would skip 7, and then I'd have 10. In hindsight, I don't think you actually need I-1. I think just this is fine because, yeah, like we don't need 2 boundaries here. We only need 1 boundary for the zeros. So that should be fine as well. Okay, and then for this part, I get the count of every number. So how many 1s are there, how many 5s, how many 10s. And then I do this prefix product that excludes zeros. So obviously you can't get a prefix product if there are zeros, because with addition, you can always subtract a prefix. But with multiplication, you can't always divide out a prefix. If there are zeros before you, then you'll have a 0 divided by 0, which doesn't work. So you have to not put any zeros in this, and you can just store the zeros separately in a map of what indices have zeros. Which I store in this tree set. And then this will store the prefix product for everything that isn't 0. That way, if I want to find a range product, you can do this with a segment tree too if you wanted, but I thought it was easier not to. If you want to do it otherwise, you can just say, what is the range product here? By doing bigger divided by smaller. And that's exactly what I do here. I brute force the left endpoint, and then I say, what is the range product? And this only happens if there isn't a 0 in this range. Last thing I should mention, modular division. We take the thing we want to divide by to the power of the mod minus 2. If you want to, I explain that really well in a separate video. So you can go look up second thread modular division, and I'll explain why. Okay. Last one is problem G. Yeah, so for this one, this is a classic tree DP. The observation here is that for any particular node, we'll do a DFS, solve all of its children, and then we'll process ourself last. And yeah, it's actually not too bad. The idea is that for some node, we might have some kids we need to keep. So if we need to keep 3 different kids, right? If there are 3 different kids, let's say you have 3 different kids. Each kid might have some subtree. Some of your kids might need to use this edge, and some of them might not need to use this edge. You can use up to 2 of your kids' edges, and maybe you can use your parents' edge. You might need it, you might not need it. But yeah, so this is kind of what's happening. And you can, like, from looking at just looking at this, you can figure out exactly whether you should use this edge or not. That's what we're going to do, and that's kind of the solution. You can also figure out whether you will have degree 2 or degree 1. That's also important. So whether you use this edge, whether you have degree 2 or 1, those are the important things. And you can just case it out. It's not actually that bad. Basically what you need to do is say, like, how many of your kids' edges do you want to use? So your kids each tell you whether they need to use their parent edge or not. If you need to use more than 2 of those, then you're in trouble, because you only can have degree 2 at maximum. So that's one way of making things impossible. The other way is for the root of the tree, if you need to use that parent, then you're in trouble as well, right? Because you can't use the root's parent, because there is no parent. that edge doesn't exist. The last thing you need to check is, like, do you run into this case where, let's say you have a node like this, right? So let's say you have one of these nodes, and this thing has degree 2. If it needs to use this edge, that's fine. You can use this edge, but you can't use an edge to another, like, let's say you're not using this edge. You can't use an edge to another kid if this is happening. So, because both of you would then be degree 2. So if one of your kids is degree 2, then you can only have one kid. Okay. Yeah, so basically, summary is, for each of our kids, we'll look into them. If the kid requires that we talk to him, it requires that, like, we're connected to him, then we need to, like, keep track of that. If we ever have 3 kids that all need us to talk to them, then it's impossible. Otherwise, if we have 2 kids, or if we aren't talking to any kids, then we need to talk to our parent. So then push up is true, and this node is a 1 degree node, just connected to the parent. And otherwise, that means we're talking to our first kid for sure. If we aren't talking to our second kid, then we're gonna look at our first kid if it's a 2 node, and we're only talking to our first kid. If this kid is a 2 node, that means it's connected to one of its kids. So we're not connected to our parent, and we're also not a 2. Otherwise, we are connected to our parent. We are 2. Okay. Last one is this. So if we're connected to 2 of our own kids, we're definitely not connected to our parent. And if if either of these are connected to one of their kids, then it's impossible, because then we have a chain of length 3. Yeah, so that's it. So all of these decisions were made deterministically. Either it's impossible or our choices are forced. And yeah, the problem is involved, but it's not, like, difficult. But yeah, it's a good tree problem worth solving. Could be a tree problem. All right. That is all for today. Thank you for watching. Hope you enjoyed the contest, and have a great rest of your day. Bye-bye.